Hey guys, and welcome to yet another fun and easy machine learning tutorial on logistic regression. To explain the concept of logistic regression, let's imagine that we want to classify whether a Pokemon will win a battle against another Pokemon. How would we classify this? Well, we could look at a set of features such as hit points, size of the Pokemon, attack rating, and defense rating. Now, intuitively, if your Pokemon has insanely high hit points, it would take ages for the opponent Pokemon to destroy yours, assuming the rest of the features are the same for both Pokemon. The same goes for size, attack, and defense of a Pokemon. So we can represent this using the equation below, where x is your features, b, also denoted as theta, are your coefficients. Now, if we just take two features such as hit points versus size of a Pokemon, we can use an algorithm such as linear regression and threshold the output. But what if we had an anomaly where the size of a Pokemon wins even though it has low hit points and is small in size? This would lead to misclassification. Also, another problem with linear regression is that it also gives values larger than 1 and less than 0. And this is where logistic regression comes in. Looking at the background of logistic regression. So, logistic regression is another technique borrowed by machine learning from the field of statistics. It is a go-to method for classification problems, despite the name logistic regression. It is not another algorithm for regression. Logistic regression is but similar to linear regression in a sense that they both have the same goal of estimating the values of parameters, coefficients. So, at the end of the training of the machine learning model, we got the function that best describes the relationship between the known input and the output values. Unlike linear regression, the prediction of the output is transformed using a non-linear function called the logistic function. Some variations of this name are called the sigmoid function as well as the logit function. The logistic function, also called the sigmoid function, was developed by a statistician to describe the properties of the population growth in an ecology rising quickly and maxing out at the carrying capacity of the environment. This is an S-shaped curve that can take any real valued number and map it into a value between 0 and 1, but never exactly at those limits, also known as asymptotes. Looking at the logistic regression equations, so the logistic regression hypothesis is defined as h theta of x, which is a function of g theta transpose x, where function g is the sigmoid function, which is defined as g of x equals 1 over 1 plus e to the power negative z. Okay, so back to our Pokemon example. If we take the hit points as x1 and the size of the Pokemon as x2 for now, we plot our data as shown over here, where x's show wins and zeros show losses. We can draw a clear line, also known as a decision boundary, which separates the wins from the losses. From this, we can estimate or predict with high certainty whether a Pokemon with a certain size or hit point values will win or lose. You may note that the gradient is quite similar to linear regression gradient. The difference is actually because linear and logistic regressions have different definitions of h of x. So the nice thing about logistic regression is that it can be used to fit complex non-linear datasets, which means we can build more complex decision boundaries by fitting complex parameters by using higher order polynomials. So how do we go about finding the coefficients of the logistic function? Well, we can estimate the values of the coefficients using stochastic gradient descent. We'll learn a little bit more about gradient descent and stochastic gradient descent in a future lecture. This is a simple procedure that can be used by many algorithms in machine learning. It works by using the model to calculate a prediction for each instance in the training set and calculate the error for the prediction. We can apply stochastic gradient descent to the problem of finding the coefficients for the logistic regression model as follows. So given a training instance, number 1, calculate the prediction using the current values of the coefficients, and 2, calculate new coefficient values based on the error in the prediction. The process is repeated until the model is accurate enough. For example, the error drops to some desirable level, also referred to as minimizing the cost function, or for a fixed number of iterations. So you continue to update the model for the training instance and correcting errors until the model is accurate enough or cannot be made any more accurate. It is often a good idea to randomize the order of the training instance shown to the model to mix up the corrections made. By updating the model for each training pattern, we call this online learning. It is also possible to collect up all the changes to the model over the training instance and make up one large update. This variation is called batch learning. A little bit more on that in a later lecture. If you look at the applications of logistic regression, number 1 is image segmentation and categorization, 2 geographic image processing, 3 handwriting recognition, and 4 we can use it for healthcare, where we analyze a group of over 1 million people for myocardial infarction within a period of 10 years is an application of logistic regression. We can use for prediction whether a person is depressed or not based on a bag of words from a corpus seems to be conveniently solvable using logistic regression as well as support vector machines or SVM. The reason logistic regression is widely used despite the fact of state-of-the-art algorithms such as deep neural networks is because logistic regression is very efficient and does not require too much computational resources, which makes it affordable to run on production. Yes, your server won't crash. If you look at logistic regression compared to decision tree, so both algorithms are really fast, and there isn't much to distinguish them in terms of runtime. Logistic regression, however, will work better if there's a single decision boundary, not necessarily parallel to the axis. Decision trees can be applied to situations where there's not just one underlying decision boundary, but many, and will work best if the class labels roughly lie in a hyper-rectangular regions. Logistic regressions is intrinsically simple, it is low variance, and so is less prone to overfitting. Decision trees can be scaled up to be very complex and are more liable to overfitting. Pruning is applied to avoid this. Okay, so that is it. Thank you for watching. Please don't forget to like, subscribe and share. Click that bell icon to get notified of more fun and easy machine learning algorithms. Also, animating these videos takes a lot of coffee, so I'll be really happy if you could support us on Patreon. Following lecture, we'll learn how to apply a simple logistic regression in Python. So see you in the next lecture. Thank you for watching.